Thanks to the organizers. My topic is evolutionary demography. And I acknowledge my collaborators, Steve Evans, David Steinsaltz, my student Amel Harati. Darwinian natural selection is a story about demographic success. Creatures pass on their genes thanks to the fertility and survival they achieve as they age across the life course. So it makes sense to try to understand the age patterns realized in demographic schedules from species to species in the light of evolution. That's why you have a demographer here. My talk comes in threes. I'm going to give an overview of three strands of evolutionary demography in a change of pace from yesterday, because today I'm outlining a broad field, and a field less familiar perhaps to many of you. So I will give a broad overview of the three strands: mutation accumulation, stochastic vitality, and optimal life histories. Then I want to tell you about the implications of one mathematical result about mutation accumulation, giving you a flavor of what is being achieved in the field. And I'd like to end with prospects for resolving a central open question and perhaps opening up discussion in this meeting, a question that seems to require combining the different existing strands of research. A few of the references include some older work between Zeus and the salmon, Zeus being an exemplar of someone who lives forever, and the salmon an exemplar of a creature that dies immediately after reproduction. There's a long history of biodemography, and I will draw on recent mathematical work with my collaborators. So in a preview of the three strands, what are we talking about? Mutation accumulation talks about similarities between flies and me. Stochastic vitality talks about differences between you and me. And optimal life histories talks about differences between elephants and you. What is it that we're trying to explain? Here is a slide of drawn from a summary paper of Shiro Horiuchi's of demographic schedules. What are schedules? These are graphs of logarithms of age-specific death rates, so measuring on a log scale with age on the horizontal axis. These from studies of large populations of 6 different kinds of organisms. Theory I'm talking about can be applied to fertility schedules also, but I'm going to concentrate on mortality, and I'm going to concentrate on adult mortality. And so what you see in this slide, which is intentionally hard to read, it's intentionally hard to read because I want you to look just at the big shapes, the impressionistic picture, not the details. You see in each of these cases a long straight stretch on a log scale, meaning exponential increase in mortality rates, a familiar pattern from 1825 from Benjamin Gompertz. The Gompertzian mortality stretch, sometimes starting off with some other things happening in developmental and early ages, but picking up in each of these species, in each of these populations. Humans, some set of humans from there, Mediterranean fruit flies, subject propelled into interest by the study by Jim Carey of 1 million Mediterranean fruit flies, enough then to measure at these extreme ages and extreme low survivals. C. elegans, a population of wasps, Drosophila, and beetles, and now you could have many pages of such schedules, not all of them like these, but a fair number of them like these, with a Gompertzian rising pattern, and then a tapering or a plateau at extreme ages. Now, it's, as I say, purposely hard to see the labels because we want to think back from the labels. The axis labels are very different. We have for humans age in years, and for medflies age in days. In fact, all the others are ages in days, but at different stretches. Ever since people started thinking about this, we realized that there are fast life histories and slow life histories. The timing is different, and yet we see in these populations regularities in shape. And so what I'm talking about today are three strands of theory that talk about why there should be regularities in shape. So the first of the theories, and the one I'm involved in, is mutation accumulation. The subject's a little complicated, and as a Cal man, I went to Stanford and wanted to simplify, so I tried to attribute the idea to William Shakespeare, who wrote, "The rain, it raineth every day." Okay, so I want you to picture all your ancestors on the pilgrimage of life wearing their fathers' woolen jackets, heavy and wet from all the rain, but drying out in spells of sunshine. In this metaphor, the rain is the reign of not so good, deleterious mutations, generation after generation. And the sunshine is natural selection, drying away the raindrops. The woolen jacket is your genome that you're carrying around, and the weight of wet is genetic load. Okay, that's the picture of mutation accumulation. The idea may not have been so clear to William Shakespeare, but became clear to Sir Peter Medawar. There he is. He saw aging as an unsolved problem in biology. Each of these three strands I'm going to try to illustrate with a schematic diagram, and then I'll come along with some words to go with the diagram. So in the heavy black line of this is a survival function, the probability of surviving. In this case, we're going to start at age 15, post much of development. And the lighter black line then is a survival function one might see if every site were wild type in the genome. And most of mortality came from exogenous forces, predation, accidents, other things. An idealized picture, if there were everything good in your genome, creatures would still die. But now you see these raindrops coming down from the top. There are the raindrops, and each raindrop carries an age-specific effect on a survival function. Now, what we actually do, we take the logarithm of the survival function, and minus the logarithm is called the cumulative hazard function. Its slope, when it is a slope, is the hazard function. What we're doing, we're thinking of each mutation as dropping an increment onto that cumulative hazard function. So reducing survival principally at some range of ages. And so the raindrops over here, those, let's say that one, is principally affecting some young ages. The raindrops over here are principally driving survival down at older ages. Well, the ones that drive survival down at young ages are very costly in selective terms. You lose a lot of potential reproduction from those. And so natural selection over the generations drives the sunshine, driving away those mutations, and there they are evaporating, not in one generation, but over many generations. And so you get fewer of those raindrops at early years, lasting in that heavy woolen coat, the genetic load you're carrying, and lots of raindrops where you get out and there's little reproduction left to lose, you have then little force of natural selection. It takes a long time to clear those raindrops out, dry out that part of the coat, and therefore more of them linger. So Brian Charlesworth, who pioneered this subject, the demographic connections to mutation accumulation, described it, saying the theory refers to the fact that deleterious alleles with effects restricted to late stages of life equilibrate at higher frequencies at mutation selection balance. If an equilibrium between inflow and outflow is achieved, they equilibrate at higher frequencies than alleles that act earlier. Notice the word restricted in this quote. It will be important later. So, the theory posits large numbers of deleterious alleles with very small age-specific effects on survival. And natural selection is weeding out more slowly the bad alleles that only or mainly affect you in your days for procreating, parenting, or for my generation, grandparenting, are running short. So ages of reproduction and nurturing that may promote the continuance of the genes, and you leave those that act later, more of them at mutation selection balance. That's the basic idea and story of mutation accumulation. Now, second strand, stochastic vitalities. Stochastic vitality, I said, is talking about differences between you and me. Stochastic vitality is a life course process. And in this picture, you see that those squiggles, those are random walks in this version of the model. And they're how good you feel, how well your body's doing, vitality, some measure of vitality. And it bounces around, but in this random walk, there's a downward drift on top of the random walk. And eventually, you hit that threshold at the bottom. Threshold's coming up toward you as you're going down to meet it. And when you arrive at the threshold, as they say, you cross over. That's the point of death. And so in this model, someone had a vitality path that went down fast and died early. Around the age of 20, someone is living up to the 70s in this story. Now, these are randomly generated profiles, but I caution you that I generated them randomly, and then I went on and on to select some that actually looked random. So now they're not really random profiles because, of course, random profiles don't look random when they come out on graphs. Okay, so this is a story, physiological story, and there's the basic idea is that differing genetic endowments and vagaries, random features of development, create heterogeneity in physiology and susceptibility to environmental shocks. And there's a long tradition of looking at this in a stylized way, going back to Jim Vopel, Ken Matten, and Eric Stallard in the end of the 1970s, who had fixed frailty. You came with a little number, you were born with that number, and that number then multiplied your hazard rate, your probabilities of dying, at every age forever in a proportional hazards framework, and that's been used very widely in demography to model unobserved heterogeneity. Now, stochastic vitality is a generalization of this fixed frailty. Vitality changes across life in some stochastic way, usually in a Markov process, and when it hits bottom, you die. So you may start off with different levels. That's like the Vopel-Matten-Stallard fixed frailty, but also things change, partly from physiological insults and nutrition and all the kinds of experiences you have, your vitality changes. Now, these models for stochastic vitality come in two flavors. Ken Manton, Anatoly Yashin, and a group largely at Duke and around them have developed rich, high-dimensional representations of vitality. Some unobserved components, lots of observed components. The state space is a suite of physiological indicators that are measured in longitudinal surveys. These are called stochastic risk factor models, and they estimate transition rates for this Markov process, for these Markov processes, from longitudinal data sets, largely from the Framingham study. So you have a rich physiological description of this changing vitality. There's another that can help with actual forecasts of relationships between physiological indicators in later life and has a lot of biomedical implications. For our general quasi-philosophical inquiry in what causes shapes for demographic schedules, these models are really quite complicated. And there's another strand that looks at simple stylized models, like the one I gave you, a Brownian motion with drift hitting a barrier. And then you look for generic properties. And Otto Allen and my collaborators David Steinsaltz and Steve Evans have applied Markov theory in nice generality. And what they show is that plateaus in hazard rates are a generic consequence of this kind of Markovian framework. Some of the simpler models also give you Gompertzian rise at main adult ages, but they all settle into quasi-stationary states eventually, and those quasi-stationary states give you a plateau in mortality. So just as fixed frailty will give you a kind of tapering off as only the most robust individuals are left to be dying, your rates level out, so stochastic vitality gives a generic explanation of the kinds of phenomena that we see. It's going to be one of these overdetermined systems where we're going to have several processes, several stories that might account for the similarities in shapes. The third main strand is optimal life history theory, and this one most of you in the room, I'm sure, know about. That's the classic piece of evolutionary theory. And so I'm picturing it with a bank statement or a ledger. Here's the bank of life, and you have an account, and you have some kind of energy balance. Your capital, if you can stand the word capital, whatever it means. And in each age range, you allocate, you make investments in growth, in maintenance and repair, in reproduction, and you get some credits back from your earlier investments and from possibly social transfers from other individuals in and out. And so you keep making these investments, and depending on the size that comes from growth and your state of repair and how much you've allocated to reproduction, your mortality rates as well as your fertility rates will respond to those investments, and you choose those investments to end up giving you the largest reproductive success. So, as I say, most of you are very familiar with this, and it's a huge subject. But very briefly, there are many different directions that optimal life history theory can go. And these trade-offs in making adaptive trade-offs over the life course, they could be programmed into the genome, or they could be implemented as dynamic behavioral responses, perhaps shaped by the kinds of cultural evolution that Mark was talking about yesterday. They could show up still in genetic variation in the forms of antagonistic pleiotropy, genes with good effects at some ages, and the same genes with multiple pleiotropic effects, good at some and bad at other ages. Or, that should be an or, they could be found in norms of reaction that are established by alleles that have gone to fixation long ago, fixing and structuring the terms of the life course. And a lot of demographic work has been influenced by Tom Kirkwood's disposable soma theory and emphasis on growth maintenance, reproduction, and repair. The demographic side of this enterprise, very specialized piece of general life history theory, and what really got going with work of Arthur Robson, who's here today, and Hilly Kaplan, and then Annette Bowdish at Rostock, and Cyrus Chu and my colleague Ronald Lee. And much of this work has emphasized roles for intergenerational and intergroup transfers in social species. So a lot of the demographic work in this broader subject has been focused on the benefits of sociality, and in this case, requiring pro-sociality if there is sharing and support, some of it between close kin and some of it between sharing groups. And analysis of the returns to investment in different background environments especially gives us insight about those x-axis scales that we saw, the differences between advantages of fast lifestyles and slow lifestyles, between long pre-procreative spans and short pre-procreative spans, rapid development, short development, a lot of it in response to environmental challenges and in response to the different allometric scaling relationships associated with size and metabolic rate. So understanding the differences among species must surely largely come from the third strand. But with respect to understanding the commonalities, there's a challenge here because by and large, these optimal models will give you nonsense if there are no constraints. Of course, life is full of constraints. Nature is all about constraints. If you don't have constraints, you don't get anything else. So as a researcher, you have to put in constraints. Very hard to measure the constraints in nature. So as a researcher, you can't usually take them from nature. You have to take them from your head. And how do you take them from your head? Well, mostly you have to take them from your head to get something sensible coming out. So as a descriptive tool, you understand what constraints you have to put in order to get out the life histories that we see. But the mathematics isn't giving you predictive power. It's very hard to be surprised in this field, unless you go to sleep and forget what you did the night before. So essential for understanding these differences, and there are huge differences among species, not so powerful as yet for understanding what might be the source of regularities across creatures with totally different body plans, totally different environmental niches. This ends part one of the talk, a quick overview of what demographers are doing in the realm of studies of Darwinian natural selection. Now I want to become more specific, talk about something I do. I work with my friends Steve Evans and David Steinsaltz on mutation accumulation. And this draws, as I said, on work of Brian Charlesworth and a paper that set us thinking, which Brian did in 2001. He assumed a simple mutation accumulation model with three main, this is what I want, assumptions. I don't see my piece, but you can read it up there. So he had a linear approximate theory for mutation accumulation. I'll explain what that means in a minute. And then he had mutant alleles with effects restricted to all ranges of later ages. So there was some mutant allele that only started troubling you when you were 20 and up, and some that only started troubling you when you were 50 and up. Nothing, and then it kicks in. And with the thought that way back in time, natural selection was able to arrange to push back certain bad things like cataracts and hearing loss, which I have, other things till it didn't matter too much. So no effect. So what you have in the mutant allele effects are nothing and then something. And you have, in Charles Worth's vision, a heavy background constant exogenous mortality from predation out when nature was brutish and life was short. And Charles Worth pointed out that these could combine to imprint a Gompertz-like exponential pattern on mortality rates by age. And what's the idea? Let me go back to that picture here. Okay, so that first curve there, all you've got is external mortality, a kind of constant background level of being eaten by tigers. Well, a constant background level turns into an exponential survivorship function, and then integrating an exponential, you're integrating an exponential. So with fertility that stays reasonably high for a while, you're going to then get exponential losses in in net reproduction. And then those exponential losses are the force that's driving natural selection. So those exponential losses, they're exponentially decreasing losses as you go out, and that's going to produce exponentially rising mortality. So it's a very straightforward, stylized idea. Now, I should say, it's not the only idea for explaining Gompertz mortality. There are libraries. I don't go to the library anymore, but I think they're full of these explanations. But many of them put exponentials in somewhere in the math in order to get them out. If you look at something is already going in exponential, and then exponential mortality comes out. But Charles Worth is putting in something constant and getting exponentials out. And it's the kind of thing you could imagine within lots and lots of special movies about different creatures. It's something that happens all over the place. It's not specific to the way humans function in Irvine. Now, so this was a good story. We caught on to it, and then we tried to build on Charles Worth's work. And bad news happened. So, mutation accumulation is intrinsically a nonlinear process. And that's because if you lose net reproduction from one mutant allele, there's less left to be lost by another mutant allele. Right? If something is killing you off at 40, then something that kills you off at 20, you've already lost your reproduction above 40. So the effect of something bad at 20 is less. It's the kind of interaction is the whole point of the story. And if you're trying to reshape whole mortality schedules, you don't have just little blips on this. Each one of the influences is a little blip. But when you add them all together, you're trying to create the shape of it. So the total effect can't be small if your theory is going to say anything. Story about a lot of little effects, but they've got to add up to something big. So you can't just make linear approximations. Charles Worth knew this, and he studied it, but it took a fair amount of work to put together a full mathematical model. And so I'm not going to talk about the model here, but if you want a model, we have an American Math Society memoir, and if you love dynamical systems, this is the book for you. Here I'm not just going to talk about meaning, not about equations. So what's the meaning of this? Well, what we found is if you put the Charlesworth story into a model that takes full accounts of population heterogeneity and of these intrinsic nonlinear interactions, the whole logic of the process, then you destroy the equilibrium altogether. So there's a kind of unraveling or meltdown, if you want. You have alleles. There's our original survival function up there. But as that rain comes down, you lose the upper range of net reproduction. Then those alleles that are hitting you at the next younger age have little loss to keep them in balance. And so they drive you down further, and you keep driving down further. And I got bored with graphing, but eventually that curve just drops. At the lowest stage of reproduction, you die. Now, if you have infinite reproduction at the lowest stage of reproduction, I guess your population isn't extinct, but the Charlesworth story unravels. So this was a striking result. It's a little like Müller's ratchet that applies in very different contexts, but what it tells us is we have to think about evolutionary processes that will avoid this. It's not a story that this happens, it's a story of this was a challenge and something in our story has to give. So what has to give? Just a little Scrabble game. We replace the word restricted by the word concentrated. We're talking about alleles restricted to late ages compared to alleles whose effects are concentrated in late ages. We say that all of these processes, or enough of them to dominate the picture, have some early age signatures. So whatever is going wrong with you, mostly it happens at late age, but sometimes it happens at early age. That's enough to hold these alleles in mutation selection equilibrium. And the benefit you get is that if that's happening, then you're building in plateaus at late ages. The early age signatures, which come, of course, to dominate, then mean that your mortality can't, in most cases, go on forever. It levels off. So suddenly we have a story which forces on us something that we were trying to explain. Instead of being an option, it's a kind of obligate feature of these models. Now, I find this quite striking, and I think we're onto something, and it's a good something that we're onto because it tells us what to begin to look for in small deleterious alleles. Now, if the small effects are small, we're not going to observe them directly, but new genomic work is giving us a lot of information about how diverse and how private are the variants that we see, going from single nucleotide polymorphisms, SNPs, to single nucleotide variants, things that you see in less than 1/1000th of samples. And there's new big sequencing work showing that there are an awful lot of these. They don't seem to have strong signatures of natural selection on them. This theory talks about how ancient those should be, how many of them affecting mortality there should be in total. And so we have some attempt to confront mutation accumulation theory with what's coming out of the study of private alleles single nucleotide variations in the genome. So that's, I think, an achievement, and that's part 2 of the talk. Now I want to come back to the challenge. So, human mortality rates have dropped a lot in recent times. What's recent? 10,000-year explosion from my friends, or 100,000 years, or 10 years. Take your interpretation of recent. There's been a lot of drop. Now, evolution shapes schedules only through effects on reproductive and nurturing ages. And for humans today, those are no longer late in the lifespan, although they were over much of evolutionary time. And Kristen Hawkes and others, the importance of grandmothers to evolution. I accept all that, but it won't carry you out with genetic effects being shaped by natural selection directly at extreme ages. There has to be some kind of story about how earlier age effects still leave their imprint on later effects, and those have to also put in that as we've made the environment, recreated our environment around us, mortality rates have dropped, so there's got to be a transformation away from the evolutionary story. And most of the ways you think about this, you'd think that mortality rates would end up today as very funny functions of age. All kinds of special things that affect you, and there's some antibiotics come in here, and there's just, the fact that these are so regular is really quite remarkable. So you'd think this enterprise was hopeless, because you'd think that once progress got in there, that come in so many forms that these things would just bounce around and there'd be as many old age schedules as you could imagine, but we see that there's not. So the question then is, how, as mortality rates drop in humans, do we get signatures imprinted over evolutionary time at earlier ages showing up in regularity at late ages? This is a problem for all strands of theory, and I haven't solved it. So I'd like us all to think about it. And what I want to do is give you one framework for thinking about how we might try to have a consistent story. So I call this sink or slide. So here are pure Gompertz schedules, exponential functions. I haven't put the plateaus in. It's just the Gompertz piece of it. And you see mortality dropping by age at every age there, not in the slope parameter of the Gompertz. Gompertz alpha e to the beta x. We're keeping the same betas. We're dropping alphas. Down comes the curve. But when you reduce the constant on an exponential function, it's the same thing as shifting it to the right. So what looks like sinking could be sliding. And Jim Vopel wrote an interesting overview paper in Nature a few years ago, pointing out that this sliding picture, the new, well, there's a thing in, what do they call it? 70 is the new 50, right? Shift in ages. It seems consistent with recent observations on human progress. So now if we think about how would we begin to build sliding into our story? Here's one idea. Let me share it with you. The alleles are ending up affecting the mortality schedule, and other ones affect the fertility schedule. We're talking about mortality. But of course, they do it through a set of intermediate physiological processes. And so if you picture a stochastic vitality model in which the transition rates are being affected more proximately directly by the alleles, and then those transition rates in the stochastic vitality end up giving you the signatures on the survival, and the signatures on the survival bring in natural selection to work on it, you have this two-stage process where stochastic vitality intervenes between what the alleles are doing to your development and what you end up with for natural selection to operate on. If you think about that, then you could imagine that recent so you could have a whole theory of this kind that works in evolutionary time, and then what recent human progress might be doing, it might be moving that lower threshold. So what would kill you if you had to live out in the Kalahari Desert, or what would kill you if you had to live around the Grotte Chauvet or something. Nowadays, you could still be coming to National Academy events. It doesn't kill you. Right? You couldn't outrun a tiger, but we don't have to outrun tigers. So the lethality threshold might drop. And at the same time, you can also imagine that with improved nutrition and other physiological advances that our reshaping of the environment has created, you could also imagine that that drift we put into the stochastic vitality models has modified. And actually, in the models, the drift and the boundary trade off. So you have a free parameter you have basically one effect that you can allocate between different kinds of processes. And so we actually know quite a bit about this thanks to the 2008 debacle, because probability theorists thought of these things as firms, investment banks heading for bankruptcy instead of organisms heading for death. And so there's a lot known in financial mathematics. All the grad students who want to go into, even now, into Wall Street are all studying this kind of thing. So there's a lot of mathematical tools coming up. But it's not simple, because simple ways create funny functions. You need more idea. You can't just sit down and do this. There need to be some real ideas for what it is about these processes that could be creating the sliding that we appear to see. So that's where the subject is today, and I end with a picture of Zeus and the salmon. Somewheres in between are all of us, and so far we seem to be heading more toward the lifestyle of Zeus than toward the lifestyle of the salmon. But of course, history is unpredictable, and so we are left with hope but uncertainty as we try to understand our own life course and what future progress of mortality might hold.